Every year, unpredicted river flooding displaces millions of people and destroys critical infrastructure. The core failure of current early warning systems is that they rely on single point sensors and isolated data. But rivers are dynamic living systems.
My name is Ryan, and alongside me are my co-founders Nema and Gitahi. We built a hybrid disaster response system. It combines a robust physical telemetry network with a deep learning predictive backend. To solve the hardware challenge in harsh remote environments, we engineered a daisy-chained spatial network instead of guessing based on rainfall alone. Angawatch deploys physical nodes from upstream all the way to downstream. Each field unit is equipped with the dual AJ-SRO4M industrial-grade ultrasonic sensors. We use dual array to confirm readings and completely eliminate false positives. But crucially, we also integrated physical flow rate sensors. We aren't just measuring the height of the water, we are measuring its velocity. This allows our physical upstream scout nodes to detect surge and speed directly at the source. But raw hardware and telemetry alone isn't enough to predict the future. To explain how we turn this physical velocity data into a 14-day predictive horizon, I'll hand it over to Nema.
Thank you, Ryan. The true deep tech innovation of Angawatch is how our AI ingests that physical telemetry. Standard neural networks view data points in isolation, but because our hardware measures both water height and speed, our AI can calculate the exact momentum of the flood wave. To process this, our predictive engine utilizes a long short-term memory or LSTM architecture. The core of our model is the LSTM cell. It regulates the flow of information through forgets, inputs, and output gates. This prevents older information from being lost, allowing the model to remember significant upstream surge events from up to 14 days ago. We also integrate a predictive layer via Meteo API, sensitizing the system with regional rainfall data 24 hours before even a storm hits. And we test this model rigorously for generalization. For instance, a model trained on the single basin logic of the Tana River failed when tested on the massive transcontinental momentum of the Congo River. That lesson in hydrological generalization ensures our AI can scale to any basin, predicting impact time at the downstream village node. With minute-level precision, Gitai will now explain how we deploy this intelligence to the last mile.
Thanks, Nema. All this intelligence is useless if it doesn't reach the people in danger. As a product designer, my focus is last-mile hardware and deployment. Each Angawatch node is equipped with a global 4G LTE module and an active buzzer siren. When our AI backend predicts a critical surge, it triggers two simultaneous actions. First, the physical hardware at the village node sounds a fail-safe local siren. Second, our neurosymbolic generative AI agent synthesizes contextual SMS alerts in local languages like Swahili. Dispatches these alerts directly to off-grid mobile phones. Furthermore, Angawatch features interactive two-way communication. Community leaders can actively text the word status to the system and instantly receive a monitor report with real-time sensor depths and forecast data. The value proposition for our target customers, governments, and disaster response agencies is an end-to-end highly scalable pipeline that costs a fraction of traditional radar stations. With a $10,000 ICA SSP price, Angawatch will transition our prototype arrays into mass-manufactured IoT hardware for large-scale pilot deployment in East Africa. Thank you to the IEEE Signal Processing Society. We are Angawatch and we're ready to protect the flood and protect the village.